All right, and the last lecture for this particular unit is on the conservation of momentum. It says any athlete knows that momentum is the most unstoppable force in sports. The only way to stop it is if you get in your own way, start making stupid mistakes, or stop believing in yourself. So, goals. Students should understand when momentum is conserved, be able to calculate using the law of conservation of momentum, and be able to predict the motion of an object in both an elastic and an inelastic collision. So conservation of momentum, very similar to conservation of energy. Conservation of energy just said, hey, energy on the right has to equal energy on the left. Same thing with conservation of momentum. PI equals PF. Now, it's not quite this simple, just like it wasn't quite that simple with the law of conservation of energy. With energy, you had to decide what energies were present, plug the formulas in, cancel stuff out. It's the same thing with conservation of momentum, except instead of trying to figure out what type of momentum is present, there's only one type of momentum, but you have to determine how many objects are present. Is there one object, two objects, before the collision, after the collision? Is it an explosion? Is it a collision? What is it? But the key thing is momentum is only conserved in a closed, isolated system. Now, what that means is if there is no friction present, because remember, friction would take away from the velocity of an object, and it's not allowed to collide with anything like a wall that is considered outside of the system. All right, this question says, if a student throws a basketball forward, what direction will the student move? This is one of the release tax questions that we've seen before. We're talking about conservation of momentum here. If you take the mass of the ball and the velocity of the ball going this way, you know that the person initially had a momentum of 0 because they're motionless. You know that if the ball moves forward, that the person has to move backwards, and that's conservation of momentum. You could also use Newton's third law. For every force, there's an equal and opposite reaction force. Okay, in this question we are given a diagram of the situation. There's no words or no narrative with this question, but you're trying to find the velocity of the cannon. So basically what we have is we have a situation where we have before the cannon is fired and we have after the cannon is fired. So we know that's going to be conservation of momentum. So we say before the cannon is fired, we consider the cannon and the cannonball to be the same object because the cannonball is inside the cannon. So really, before the explosion, I have one object. After the explosion, I have two objects. I have the cannonball and I have the cannon. I'm going to say that the PC stands for the cannon, and I'm going to say the PB stands for the ball. So we have the cannon and the ball. So those are the information we have. So we have the initial momentum, we'll go ahead and call it the total momentum just so we can keep it straight, is equal to the momentum of the cannon plus the momentum of the ball. Now, what we had before is we had a total mass and a total velocity. We have the mass of the cannon, we have the velocity of the cannon, we have the mass of the ball, we have the velocity of the ball. So now let's look at the information we have. If we have the cannonball as a mass of 10 and the cannon has a mass of 1,000, we could say that the total mass is 1,010 because you have a total mass, you put the ball inside the cannon, that's what you have as 1,010. Now, it doesn't explicitly say so, but we can assume that the velocity of the cannon is originally 0. It doesn't make a whole lot of sense to kind of wheel the cannon forward and have it shoot backwards. So in order to get the best aim, we're going to assume that this value is 0. Now, we also have that the mass of the cannon tells us is 1,000. We have the velocity of the cannon, and that's what we're trying to solve for. Now, one key thing that you want to look at is it actually has the arrow going backward. Okay, that is an indication that I should get a negative value here whenever I do all the math. Plus the mass of the ball times the velocity of the ball. When you take all these things, you multiply them out. Anything times 0 is 0. You have 1,000 VC plus 5,000. Now, in order to solve this, you need to take this and you need to move it to the other side. When you do that, you get negative 5,000 equals 1,000 VC. Divide both sides by 1,000, and what you get is the velocity of the cannon ends up being -5 meters per second. Now, a lot of people get stuck on this. They say, well, how can the cannon be going -5 meters per second? Remember, with velocity, the negative is just an indication of direction. If the cannon ball is fired at a positive 500, we would expect the cannon to go in the opposite direction at a much smaller velocity, which it does. Alright, in this question it says you have a 50-gram bullet that is fired into a 2-kilogram ballistic gel at 200 meters per second. So you have a bullet, and we're going to say that that's 50 grams, and we're going to fire it into this big ballistic gel, which has a mass of 2 kilograms. And we're firing this bullet pretty fast, 200 meters per second. And we want to know what is the velocity of the combination after they collide. So the key thing is the combination after they collide. So that lets me know that the bullet is going to stick into the gel. So what we do is we say, okay, this is obviously, we're trying to solve for the total velocity, or the velocity of them together. So now we say, okay, well, what information do I have, or what principle am I going to use? Now we know we're talking about mass and velocities, so we're going to use the principle of the conservation of momentum. Pi equals Pf. Now, when you look at it, before you have a collision occur, we have two objects. We have the momentum of the bullet, and we have the momentum of the gel. After the collision, they stick together. So we have PT, total momentum. So now let's look at our given information. We are given the mass of the bullet, and by now you should know that grams is not acceptable. So you have 0.05 kilograms. You have the velocity of the bullet is 200 meters per second. You also have the mass of the gel, which is 2 kilograms. And you should also have the mass of them together, because if you have them independently, just add them together, 2.05. It also says that the gel is initially at rest, or you can assume that the gel is initially at rest. So now we can take our version of the formula we have here, which is mass of the bullet, velocity of the bullet, plus mass of the gel, velocity of the gel, equals mass of them together, velocity of them together. So we have 2 times, the mass of the bullet is 0.05. 0.05 times 200 plus 2 times 0 equals 2.05 VT. 2 times 0 is 0, so that term is gone. And basically what you have is 0.05 times 200, which is 10, equaling 2.05 VT. Divide both sides by 2.05, and you find that the velocity of them together is 4.88 meters per second. So much, much slower than the bullet originally is due to the mass of the ballistic gel. Okay, collisions. So there are basically two types of collisions, although there's a lot of gray area in between the two. So the first one is a perfectly elastic collision. Now, a perfectly elastic collision is one in which kinetic energy is conserved as part of the collision. They're very, very rare, and they involve basically the object has to bounce in order for it to occur. And it has to bounce perfectly. There can be no deformation of the object. It can't have a dent. You can't have anything where it can't even really make a noise, because all the energy that it has to be conserved. Now that's very, very rare that you're going to have a perfectly elastic collision. Now we do assume a lot of times that a collision is elastic when in fact it may not be. The other one that you have is a perfectly inelastic collision, and that would be where two objects collide and stick together. So if you were to fire some Play-Doh at a wall or something like that, or some sort of car, or if cars collide and stick together, that would be considered a perfectly inelastic collision. Now, in an inelastic collision, kinetic energy is not conserved. So that's how you can tell the difference between the two. Okay, if you have a perfectly elastic, or if you have a collision, you can look at the kinetic energy before and the kinetic energy after to determine whether or not it's elastic or inelastic. Now, most things are usually not perfectly elastic or perfectly inelastic. Usually they're kind of in the middle. We're not going to do calculations for the middle because they're very difficult, because you have to start to look at, dents and energy of sound and all kinds of things. So we're going to classify them as perfectly elastic, perfectly inelastic, and then not for calculation purposes, but to say somewhere in between. All right, in this question it says a bullet of 0.05 kilograms is fired into a 1.8 kilogram block, and it was initially moving at 100 meters per second. And it says if a perfectly elastic collision occurs and the bullet ricochets with a velocity of negative 48 meters per second, what will the velocity of the block be? So the key thing there is it is an elastic collision. Whenever you have an elastic collision, what that means is that kinetic energy is conserved. So in other words, the kinetic energy that I have before the collision has to equal the kinetic energy that I have after the collision. Now, originally, I only had one thing that was moving, and that was the bullet. Afterward, I have both the bullet and we'll call it a ballistic gel, even though it says block. You have two things that move. In order for it to be an elastic collision, kinetic energy must be conserved. So what I have to have is 1/2 mv squared equals 1/2 mv squared plus 1/2 mv squared. Now before you get any ideas of simplifying this, realize that these are all different masses and all different velocities. This right here, remember, has to do with the bullet. And it's before. This is the bullet, but it's after. And this right here is the gel. So let's go ahead, we can cross out the 1/2 term in each case. That cancels out. So we look at the mass of the bullet. The mass of the bullet is 0.05. The velocity is originally 100. We square it. The bullet, still 0.05. In this case, it's negative 48. But when you square a negative number, it's going to become a positive number. And finally, you have the gel, which has a mass of 1.8. And then you can solve for the velocity squared. So once you do this, you say 0.05 times 100 squared, you get 500. On the other side, 0.05 times 48 squared, you get 115.2. And that means that this right here allows you to solve for this v term. The first thing that I have to do is I have to eliminate this, and how I do that is I subtract 115.2. Remember, I can't subtract 1.8 because this 1.8 is multiplied by that v squared term. So now we say 500 minus 115.2. When we do that, we get 384.8 equals 1.8 v squared. Divide both sides by 1.8, and you get 213.78. But remember, that is the v squared term. So you take the square root of both sides, and when you do that, you get v is equal to 14.6 meters per second. Now, when you take the square root, remember this could be positive or negative, so you have to decide what it's going to be. Now you could actually do the same calculation with conservation of momentum to figure out what the direction is, but realistically, if the bullet is moving this direction to begin with, and then bounces off in this direction, that means that this giant block right here is going to have to move in the original direction of the bullet. So we know that this is going to be a positive 14.6 meters per second. Okay, this final example for this unit is a car traveling 100 meters per second, I should say slams inelastically, not inelasticity, into a parked car. Each car has a mass of 2,000 kilograms. What is the final velocity of both cars? So what we're trying to figure out is the velocity of them when they are together. Now remember, inelastically means when you have one car that hits the other car, they stick together and they become one object. So, before the collision occurs, I have two two objects. I have the car number 1 and I have car number 2. Afterwards, they are stuck together. So mass 1 and mass 2 are the same number. They are both 2,000 kilograms because it says each has a mass of 2,000. I know that the first car is moving at 100 meters per second, which is very, very fast. And the second car is at rest because it says it's parked. That allows me to figure out what I'm talking about here because I can say mass 1, velocity 1, plus mass 2, velocity 2, equals mass together, velocity together. So 1,000 times 100 plus 1,000 times 0 equals, the total mass would be the mass of those added together, which would be 4,000. Should be 2,000 as well. Okay, so once you're here, realize that this term is 0 because 2,000 times 0 is still 0. And all I have to do is divide both sides by 4,000. So when you take 2,000 and divide by 4,000, you should realize that's half. Half of 100 is 50 meters per second. Now, a lot of times people say, oh, well, all you have to do is cut it in half. The only reason why it works in this particular case is because both of the cars have the same mass, and one of the cars was initially at rest. That's the only reason why this example works out to be half. In every other inelastic collision, you have to do this math in order for it to work. If you just try and cut it in half, it's going to be wrong. So by now you should understand when momentum is conserved. Momentum is conserved when you have a closed, isolated system, no friction, no outside forces acting on the objects. You should also be able to expand the law of conservation of momentum to say, hey, how many things do I have before the collision? I've got one thing over here and two things over here. Okay? You should also be able to go ahead and predict the motion of an object as a result of the conservation of momentum. So predict the velocity, predict the mass, determine whether or not a collision is elastic or inelastic. You should be able to do all of those things.